Alright, time for another draftphysics.com, debatephysics.com also. But you can't drag these people into conversation, argument, debate, whatever you want to call it, about the actual physics and what evidence they actually have to draw whatever we might call conclusions. They're dissecting a scene, okay, a picture. We're seeing some part of reality, and they're trying to figure out what it actually is going on, filling in the pieces we can't see. And I would argue they're doing it so recklessly and so sloppily, it's just all really bad science. Because they're not following any of the rules. Like, don't jump to stupid conclusions. You know, repeat experiments and all of that kind of crap. All right, so what am I looking for here? I think I'm looking for this. It should be me here. All right, so there's a Dr. Lincoln video here. It says, does the weak force do anything? So these people don't even know what the forces are. So they have such a poor conception of how reality actually works. And so I'll point that out. Oh, I can't click it there. I have to click it here.
Told you that those videos only tell you.
Don't have to yell. Anyway, okay, leave us begin. Right, can you see that adequately? Yeah. It could be moved over a little. Yes, it could. All right. So now, leave us begin.
If you watch just about any video about fundamental physics, you'll be told that there are 4 known fundamental forces.
Yeah, you'll be told crap, okay? Just stuff a certain number of people, whatever, 64 people made up. Some story that 64 people made up and everybody else is too lazy or they don't have enough time and they can't make up a better story. So it's just this silly frickin' story. So when they say 4 fundamental forces, I would argue, no, there's only one fundamental mechanism, and that is there's stuff in the universe, and some of the stuff is really small. And the fact is there are electrons and protons, that's the matter part, and then there's bits of force, little tiny bits of force, moving the speed of force. So light is a force, okay. Magnetic fields are made out of force. They're not an actual force, they're just a pattern in the force. The light is a pattern in the force at a frequency, kind of obviously. All right, and that's all there is. So there's little bits of stuff moving the speed of force that never stops, but when it does hit a proton or electron, it can stick to it and push it. But it can't push it at the speed of light. It has to push it something slower than that because it's a heavy clump of dead matter. And that's all that really happens in the universe, is clumps of electrons and protons are being pushed around by little discrete bits of force. And coincidentally, kind of obviously, in a way that makes it all work really well, so I'll just draw that real quick. It matches perfectly. So you're trying to create a circumstance where electrons and protons attract, and where protons and electrons repel. And all you really need to do that is to understand that the stuff pushing in the universe has the same character as the electrons and protons. That is, there's an electron force and a proton force. And all I have to do for this to work is to say, well, if the electron force hits an electron, it pushes it, or it reflects. Okay, and if a proton force hits an electron, it goes right through and it comes out an electron force. And so that scenario, if put into play, will mean that the electron force, an electron will always radiate green, electron force. It'll always radiate it, okay? No red will ever come out of it or reflect off of it. And the proton will end up doing exactly the opposite, which is it will radiate always red. And the simple truth is, just by the simple rules, that if the red force hits the green object, it just gets changed. It doesn't cause any momentum, so it's not a force. And vice versa, when the green hits the red, it doesn't do anything But if the green hits the green, whoops, if a green hits a green, it does either reflect, which means it hits this one again, or it sticks and pushes it, gives it momentum in the opposite direction. So you can understand that this would perfectly duplicate Maxwell's definition of charge. You'll end up with objects that are emitting a force, and all they're really doing is reflecting the universe. The universe has got a ton of this stuff in it. They're just going to reflect it. And in the case of the conversion, they're going to convert one force into the other. Now, obviously, there's just as many protons as electrons, so the force gets converted into still being an equal amount of both, generally speaking. And so the protons would repel the protons. Now, the simple argument, right, he's talking about these three fundamental forces, then you get to the strong force. And this is just one of the stupidest things in physics. I mean, I figured this out when I was a little kid, all right? So, I mean, I knew this one right away. I mean, you know, at 13, I had already figured this out just because of this explanation, just because they already knew. I didn't know how charge was being created, but I knew it existed, right? And it was kind of obvious that if electrons and protons, okay, attract each other, then why couldn't a proton be here, and an electron could be here, and another electron could be here, and why do I need a strong force? So obviously there are cases, we'll call these protons, okay, and you have an electron in between. I mean, I figured that out when I was 13. You know, doesn't that solve the problem? Oh, we can't get protons to get close to each other. Well, yeah, you can. Just stick an electron in between them and they'll stick right to it. They'll be attracted and they'll stick. They won't see each other. The electron will just hold them together. What's the problem? What do I need a strong force for? I don't need any strong force. There's almost no force at all. Yeah. So, I mean, you know, their physics is just so... So this is so simple, right? All you have to do is two kinds of matter, two kinds of force, and two kinds of interaction. 2 plus 2 plus 2, and you've perfectly described, it'll perfectly duplicate two charges and their interactions. It'll perfectly work. I've got a simulation of it. It works perfectly. It works perfectly. The electrons attract to the protons. The electrons repel the electrons. Works perfectly. So simple. And yet they'll talk all this nonsense. Let's listen to some more nonsense. I mean, they just made up all this crap, and it's a crappy theory. It's way too complicated, way too messy, and it doesn't even work. It doesn't even make any sense. You can't simulate it.
Gravity, electromagnetism, and...
So electromagnetism is just mushy talk. What are you talking about, electromagnetism? Electric is different than magnetic, so why are you smashing those two words together? The fact is it's all magnetic in terms of induction. So induction is all magnetic. There's no electrical. And electrical is just the fact that you're going to move this force through a conductor by pushing electrons. The force is actually the light. Okay, you hit the metal with the light. The metal creates electricity. Well, the electricity is really the same force the light's made out of, and now it's pushing electrons instead of flying through space. That's the only difference. It's pushing electrons. It's doing work. The force is pushing electrons through the conductor. Really simple. Really fucking simple. It's actually the light. The light is actually still light in a real way. Okay? It's still a little discrete corpuscles capable of causing electrons and protons to have momentum. Now, the reason why it's all electron-based is because the protons are heavier and they don't move very well, so they're stuck in the nucleuses, and the electrons are on the outside, so the electrons do all the interacting.
Two nuclear forces. You'll even be told how strong they are. What if I told...
Absolute nonsense. Yeah, you'd be told nothing, okay? Nothing will be explained, and it's all based on this silly MV squared crap, this silly living force of Leibniz's, this guy who said Newton and Descartes are two atheists. I mean, this religious kook's silly cult religion. And here you are, you know, hundreds of years later, and you're still writing on the same silly totem pole.
Told you that those videos only tell you part of the story.
They don't tell you anything. They don't tell you anything rational. They don't explain what charge is. They don't explain what magnetism is. They don't explain what light is in any kind of coherent or rational way. They just draw some squiggly frickin' line and say, well, isn't that good enough? No, it's not good enough. It's stupid.
Sounds like it's time to do a deeper dive.
Blah, 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 blah. Deeper. I mean, it just, it's just so, you really haven't analyzed anything. You really haven't methodically drawn these objects on a board and then said, how can I make these objects do what they do? I know what they do. How do I make it happen? And you just haven't done that. Now, the truth is, look, it took me 10 years to get this simple answer, okay? It took me 10 years of playing with electrons and protons before I figured out this simple solution. But the only reason why it took 10 years is because I had to get all the garbage these people kept saying to me out of my head. I had to stop thinking they knew anything about physics. It wasn't until I just said, start over with what you know exists, and don't pay any attention to anything they say about a wave or an ether or anything, and then just try to reconstruct. They're poison to thinking. The nonsense they tell you gets you gremlin paranoid. You just keep looking for them. I mean, once they put that suggestion in your head, it's like somebody putting the vengeful God into people's heads. It makes them frickin' paranoid. If I said to you, step on a crack, break your mother's back, yeah, even though you don't believe it, you're not going to go outside and hop on the cracks on purpose, because I've infected you with a nonsense, and the nonsense is going to be like, well, about why take a chance? I'll play it safe. It's going to fuck you up. And that's all these people are doing. They're just fucking your neurons. They're not fucking them. They're masturbating on them. But whatever. I don't want to get into the technicality. It's all very disgusting. And this is just so useless. I'm big. I'm great. We're doing great stuff. We're so fantastic. We're God to make you understand. We are doing everything. We are so powerful. We are great, fantastic. Look at this stuff we're doing. We're fucking fantastic. That's all it is. Right. So I guess I should do something here, right? Boom, bang, boom, 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 boom. Greatest video ever. Yeah, it's just nonsense. Smart people fall for this crap.
In books and articles about frontier physics, it's entirely
You could wait till the song stops.
common to be told of 4 fundamental forces. Gravity was the first to be understood.
Oh, understood. Oh, hilarious. So it's so goddamn irritating. This sorry, Dr. Lincoln, you're a motherfucker. I mean, you don't believe it's a force, so why are you saying it's a force? Why are you doing that? It's just goddamn disgusting. Okay, you're going to say it's a bent geodesic, that there is no force involved. There's no energy involved. No energy is involved in the process of gravitation. It is some sort of bent geodesic that makes it happen. So why are you playing this game that you think it's a force? Damn it. They're just so duplicitous. On top of being wrong and stupid and arrogant and showy and obnoxious, they're just goddamn stupid.
And it keeps us firmly on the ground and guides the planets through the
blah, blah. I mean, what just baby talk?
heavens. Electromagnetism is a blend.
So again, I'll just do gravity real quick just to say, oh, look how simple it is. And the dopes can't figure it out. All right. So they have a simple problem. So Richard Feynman sits there and goes through this and he illustrates mock gravity, or what you could call Lesage gravity, or what you could call Fadio gravity. The idea that gravity is made out of a corpuscle with momentum. Okay, so you have a very simple idea that the pressure is in the universe. Okay, the universe is full of something called pressure. Okay, in the form of these little arrows that I just already pointed out. and they're going to hit electrons and protons. So the only thing there is these arrows, okay, are little quantas, little bits of light quanta, as Einstein would say, little bits of force, and then you have the only objects that are in the real universe are electrons and protons. The plants are made out of these, okay, the people are made out of these. These are the only things that really do anything in the real universe. The real universe is empty space, okay, distance between little bits of momentum traveling the speed of light, and objects called electrons and protons that do absolutely nothing but be forced, okay, by these force bits. They're forced by the force bits to be pushed around. That's the actual universe. And so what really happens is that when you have an object that has a bunch of these little electrons and protons in it, okay, you might be able to understand that they get momentum from half the force, right? The green force is giving the green things momentum, the red force is giving the red things momentum. So the force comes in, okay, it interacts with these bits and pushes them around, okay, pushes them in the direction that they get hit by. Now, obviously, they can only get hit by this kind of direction, okay? I can't hit this side of the earth from here. Can't do it, right? I can only hit stuff going this way. I can't hit stuff going that way. I have to take a pause. All right, so Feynman would, he would draw it this way. You could say there was two objects here, and one object would essentially be shielding this object from ever getting hit by the force, because this is going to end up hitting stuff inside of here, and so there's going to be less force going this way and less force going that way. They're going to be pulled together, but that's not the important feature. The important feature is where they say there's a flaw in this theory, because if stuff can be pushed by this force, then every time you moved in a direction, you'd move into more force. You can understand that if I moved this way, I'm going to hit more bits of force this way, and there's going to be less bits of force hitting me from this way because I have a speed and I'm running away from them, so I can't get hit by them because I'm running away from them. So it would be a drag problem. Now the fact is this nuclear physicist should know, yeah, electrons and protons are in fact dragged. We don't get hit by electrons and protons all by themselves flying around in space. They don't do that. Okay, they can't make it. They can't fly through space. I can't shoot electrons and protons from the space shuttle to the moon. Can't do it. They won't get there. All right, so drag is an actual function. All right, but the real important part is that what do you see? What happens to the Earth? Okay, so you hit a force this way. What happens? Well, you move something this way. Well, what's happening on the other side? Well, you're moving something this way. Obviously, the two things can't both win, so they have a tug of war, and so everything's constantly being jiggled. So you're moving matter from here, and then you move it over to here. And then the force from the other side moves it back over here again. And then this force moves it back over here again. And then this force moves it back over here again. So what are you doing this whole time? Well, you're going slower than the speed of light. So now your force that went in at the speed of light, that was moving the speed of light, isn't going to get where it was going. At the speed of light, it was going to be here in 1 second. Well, because it's moving matter back and forth, now it's only going to get here. So you've taken some of the energy out of the photons, essentially, because now they're not going to get where they were going. They're not going to move the distance at the speed of light because they're pushing matter. So all this pushing matter is what? It's called heat. What's in the center of the Earth? Oh yeah, a bunch of hotness. Okay, so it's just so obvious what's taking place. You're jiggling matter. Jiggling matter is using energy. That's why more force goes in than force comes out, is because you're using the force to move matter, and you're not moving it anywhere. You're moving it back and forth and up and down and forward and back, but that's all you're doing. You're moving it a bunch of nowhere. You're not going anywhere, but you are moving it. Just like you're moving into the ground right now. Your ass is moving into the ground, and the ground has to actually physically push you the fuck back up. It rejects your existence. You impose on it. You dent it, and it pushes you back up. You are falling literally into the earth, and the earth is literally pushing you back. Those are two actions that require you to absorb energy. You can't do that without using energy from some source. So obviously that's why more energy goes in than energy comes out. Stupid. Yes, anyway. I mean, is that complicated? No. Should they have thought of it? Yes. Duh.
of electricity and magnetism first really understood in the 1800s.
And it wasn't really understood. So again, this is more bullshit. You can't draw a picture of any of it. You have no clue what the exact mechanism is in any way whatsoever. Now, the simple argument, it's just a pattern, just like photons, except the pattern is a bullseye, of red and green force, and only things that are a dipole can see the pattern. So only things that can see the bullseye can react to the bullseye, that kind of argument. It's just a pattern in these little arrows. That's all you're doing. You're creating. I push my hand. Okay, what did I just do to the universe? I pushed a bunch of photons. I made them reflect sooner than they would have. I've changed their density. Okay, so if they were coming at me with a distance of 1 millimeter between them, and I push my hand, well, then they're going to leave with a 0.5 millimeter between them. I'm going to increase their condensation. I'm going to compress the space that they're in. Those are the patterns that are electromagnetism. They are not two different forces. It's not even a different force. It's just a different pattern in the force. The force moving the speed of force, not the speed of light, the speed of force, because all force moves that speed.
But it also explains how light works, as well as playing a key role in chemistry.
No, it's just amazing they say this crap. They have this silly diagram of a photon. They don't recognize the fact that it obviously has gigantic polarization. An electron could never produce, one single electron cannot produce a whole photon because its polarization is gigantic.
The strong nuclear force is the one that holds protons and neutrons together.
So big bullshit, right? You don't need any force at all to do that. Not any force at all. Just stick an electron. Say a neutron is a proton and an electron. You're just saying, okay, I just put another electron on the other side of the neutron, and I have a perfect mechanism. Indestructible almost mechanism. In the sense that I have two protons right next to each other, and I have a perfect little electron right between them. Problems entirely solved. No strong force required.
In the nucleus of atoms. Without the strong nuclear force, the only element out there would be hydrogen. And, of course...
So, says you. So more nonsense. Okay, he's just talking about how you build a nucleus. Okay, we already know that, obviously there's lots of capacity to build these nucleuses, and if you convert the neutrons into electrons and protons, then you can really understand why the nucleus is positively charged, because the neutron is got an extra proton, right? So you put protons with the neutrons, you have twice as many positive charges than you have negative charges. That's why the nucleus is positive.
There's also the weak nuclear force, which is frequently mentioned as being responsible for some radioactivity. I made a video that explains...
Yeah, you didn't explain shit. It's just such nonsense. Z particle and the W particle and the... It's just such baby talk. God, it's just so bad.
Explains why that's only part of the story. The link is in the description below. When authors and video creators list the forces, they order them in terms of how strong they are. The usual list says that...
So it's just kind of silly because there's one universe. So again, let's just point out, there's only one universe. It's the universe where electrons and protons exist. And from their perspective, all of this stuff is the same stuff. Okay, there is no gravity is a very weak force. No, it's a very strong force, okay? Every time an electron moves, it's creating gravity. It's absorbing the energy of a force. Too frickin' silly.
The strongest of the forces is the strong force.
So again, no evidence that you need any such thing as any force to push protons together. Even if you thought of neutrons as being neutral, you could understand, well, if I stick a neutron between two protons, I don't need any strong force because the protons can't see each other anymore. They're blocked by the neutron, so obviously, what's the problem? Why is it hard to get the two protons close to each other if there's a neutron between them? So again, they're so illogical. It's such a simple solution. And there's not some catastrophic failure with the idea. I mean, even if you don't believe in this, that a neutron is made out of a proton and an electron, and you just believe it's some sort of magical neutral thing, you could understand, I don't need a strong force to push a proton next to a neutron. And why would I think that the protons could see each other if they're on opposite sides of the neutron? How could they possibly reject each other when they don't see each other? I mean, that's really not stretching credulity or reason. And they never even consider it.
Call the strength of the...
What the fuck is this image? What the fuck is this shit? This squiggly shit. And these 1942, HTML drawing. What is this? This is the best you could do? The graphics team? Oh, I mean, they must have been watching the Super Bowl, huh?
Strong force to be the basic unit, we can say that it has a strength of 1.
Oh, it's just pitiful. This is pitiful. So again, it's just not acknowledging that obviously the only place we deal with gravity is on this hugely big scale. But the fact is if you had to make it out of photons, you need just a huge number of photons. You need a huge number of anything to get the same effect.
Then, each in turn, we say that the strength of electromagnetism is about 0.01. The weak force is about 10 to the minus 5th power.
So again, does it really make any sense to you? Just saying. Why is there a difficulty in getting protons close to each other if I can shove something between them, that's inert? That makes it impossible for them to, spit their acid at each other. If they can't see each other, they can't repel each other.
And gravity is the paltry 10 to the minus 40 power. And that's the...
So it is sort of ridiculous, right? Because like I just say to you, I mean, obviously it's one hell of a strong force if it can move an entire Earth. I mean, fuck.
Story we tell. Of course, if you think about it for the tiniest moment, you realize that this simple statement is utter hogwash, or at least it's an incomplete telling of the tale.
Why do you keep doing stuff like this? It's really annoying. Because your telling looks just as stupid as what you just did. So now, why are you giving us this stupid diagram and you're not saying ahead of time, here's the stupid diagram? I mean, but you just wasted my rhetoric, right? Because now you're going to say something, you're going to say some other dumber version, and now I'm going to have to debunk not only the thing you think is garbage, but now I'm going to have to debunk the garbage you're going to spew.
After all, you've lived your entire life, and unless you're a physicist, you've never encountered the strong nuclear force, and you have plenty of experience with gravity.
Well, that's really not an argument of any kind. We know that science is tricky. The little stuff is little stuff, and yes, you can't shake its hand, you can't really watch it, you can't see it, you can't do anything, because if you do anything, you'll bother it terribly.
Your day-to-day experience tells you that gravity is way more important than the strong nuclear force. So what's the deal?
I mean, you can't even draw that conclusion. Why would I even attempt to draw that conclusion from my perspective? I mean, I know the proton is an apple to the earth. I mean, I know that I can't possibly know what its life is like. It's so much smaller than me.
What it boils down to is that the different forces have different behaviors. The way that the strength of the forces change with distance isn't the same. To illustrate
some more mush. It's all inverse square law, so that's all kind of bullshit, but whatever, blah, blah, blah. Let's see where he's going with this nonsense.
The idea, suppose there were two hypothetical forces, one that is very strong for close distances, but gets...
Okay, so again, this isn't anything to do with reality in the sense that what he's going to do is instead of understanding exactly why, a force gets stronger or weaker, he's going to just talk some bullshit because he doesn't really think in terms of the real universe. You have to, if you're going to be a physicist, you really have to train your brain to think, oh, the universe I'm in isn't the real universe. There's a bunch of empty space everywhere here. and there's just electrons and protons that are doing all of this. All of this stuff is made out of electrons and protons, and anything that moves, anything that happens to the electrons and protons first. They do everything first. Okay, everything else is emergent. All right, and so what he's really talking about here is that you have a positive nucleus, okay, and then you have electrons. So obviously, when you approach this, let's say I had another electron here. Okay, when you approach this atom, the trick is from a distance, these forces are going to be very weak, and this is going to be very strong. But as you get closer, especially if you're negatively charged, all of a sudden you're going to be very attracted out here, because this is positive, you're negative, and this is a weak force, and this is a weak force. But as you get closer and closer, because of the inverse square law, these forces get stronger and stronger. And so does this one, but it doesn't get stronger enough compared to these two forces getting stronger. So because of the inverse square law, all of a sudden at this location, it's repulsive. So at this location, you're repelled. At this location, you're attracted. Okay, but it's only because of the composition of the atom, because at different locations, it's going to look different. If I came in from this direction, the electron is blocking the proton partially, and that's another argument, right? The further away this electron is, the more it blocks this out. So if I was close to the electron and very far from the proton, I wouldn't even see it. So all I would know is the repulsion. But if the electron was right near the surface of the proton, I don't even see the electron. All I see is the proton. So all I get is this red view. So it's all about it turning from blue to purple, right? So if this was red and blue, you could understand all you're really doing is saying at places it looks purple, at places it looks blue, at places it looks red. I mean, I'm sorry, but this is this is the Occam's razor squared. Okay, I mean, it's so simple and it covers the subject. It explains the phenomenon.
It's weaker for long distances, while there's a second force that is weaker at short distances but doesn't change. In this situation, one force is stronger than the other at short distances, while the other is stronger at long distances.
So it's the same force, and all you're doing is saying, what am I closest to, electrons or protons? And what's the differential in distance between the electron and the proton? So you're really just saying, look, here's my finger. I can block my whole frickin' head, okay? Or I can make the finger almost irrelevant. It just depends on proximity and where you are viewing the proximity.
You can't say which one is stronger without more information. For the list of strengths I mentioned earlier, the distance that was chosen is about 10 to the minus 15 meters, or a femtometer. That's about the size of a proton, which is, of course, super, super small.
All right, so we know they can't do any of this stuff, all right? They can't measure any of those distances. This is just such bravado to say they have any video of that.
But it's the size at which particle physics experiments are done, so it makes sense.
No, it doesn't make any sense, and it's the whole idea of calling it particle physics when you don't even believe in particles is just so fucking irritating. It's just so irritating.
Let's talk about each force in turn. Let's start with electromagnetism and gravity, because both of...
So why would you... Let's talk about each force in turn, and then you throw the two of them in the same category.
These forces act the same way. They both weaken as the square of the distance between two objects.
Yeah, all of them do that. But they don't do it when you're talking about a composite object that has pluses and minuses in it. If it has pluses and minuses in it, then it depends on where you're coming at it from. Whether you're facing an electron or you're facing the gap between electrons. But it's all inverse square.
Double the distance, and the force goes down by 4. Triple the distance, and it goes down by 9.
Same for photons, same for the sun, same for lots of things. Anything that is a point, anything that can be reduced to spherical symmetry is the inverse square law.
If you've heard about Coulomb's law, which describes the behavior of electric forces, and Newton's law of gravity, which handles, of course, gravity, you can do this yourself. Now, there are some subtleties here. The K variable in the Coulomb equation sets the strength of the electromagnetic force, while the G term sets the strength of gravity.
And by saying the strength, you're just really in a way saying what's the density of the force. So the G factor is really just telling you how dense is the force. That's the part that you're really, that's the part that the inverse square law is really changing, is the density of the force.
But both of those depend on the units. The unit of electric charge in case of electromagnetism, and mass in the case of gravity. We can see what that means by looking at the ratio of the force of gravity and electromagnetism between two identical particles. We take the two equations, take the ratio, and we find that the ratio between gravity and electromagnetism doesn't depend on distance. It's the same everywhere. What matters is the charge to mass ratio, and this isn't a constant. For example, take
All right, the charge to mass ratio is a constant if you're using elementary particles.
the electron and the proton. They have the same amount of charge, but different mass.
Well, there you go. And, this different mass thing is really a question about it moves less. You could argue. It's harder to move. So we don't know for sure that it's really a mass issue as it is some sort of feature that the proton has that makes it harder to stick force to it.
So, for two electrons, gravity is 4.2 times 10 to the 42 power times weaker. But for two protons, gravity is only 1.2.
So again, the gravity is the charge, okay? Charge is the function that's moving the electrons and protons. It's obviously consuming the total force. So it's just kind of a nonsense to make this argument because charge is causing the motion. The motion is consuming the forces, a portion of the force's energy, and that's the residue of that motion is an absence of force in the direction of the motion. So obviously when I'm pushing force, I'm adding pressure. When I'm expanding it, going the other way, when I'm doing this, I'm relaxing the amount of energy.
Times 10 to the 36 times weaker. The second is nearly 3.5 million times bigger than the first.
All right, so I don't even know why they bother with this. What use is this moronic nonsense of trying to first change them into different forces when they're basically the consequence of exactly the same event, which is the motion of an electron or the motion of a proton? And the simple argument is that yes, okay, the effect you have on the entire field, okay, of energy in the universe is obviously, if you're going to compare the amount that I'm moving with one hand to the entire universe, well, yeah, it's going to seem like nothing. So that's how they're cheating the argument. They're really making a comparison that, well, if I just look at my hand, if the only thing being analyzed is my hand and this little bit of space, then I'm going to look like I'm really powerful. But if I'm going to compare it to the entire universe, then I'm going to look really weak.
And that's how one compares gravity and electromagnetism. The strong force is different. For example, its strength has a very different dependence on distance. If two objects that are capable of experiencing the strong force...
Again, I don't even know why they're talking about anything called the strong force. Why are they bothering? There is no need to create some external force that pushes protons together when all you need to do is stick an electron between them. He's making a face at me.
are very close to one another, they feel very little force between them. However, when they get about a femtometer apart, which is about the size of a proton, the force gets stronger, rising to about...
All right, so that's just idiotic, right? I think anybody rational can understand there's no way the force gets stronger. So there's no way the proton, as it gets further away from another proton, the force gets stronger. I mean, it's just so fucking ridiculous. And they're just making this up, right? I mean, they can't see any of that. So I don't know what piece of nonsense experiment makes them think protons gain velocity as they get further away from the thing they're running away from. They obviously, just like magnets, just like he's basically saying, I put two north magnets together and then they push each other apart. And he's basically saying that somehow when they're this far apart, this goes even faster. That somehow it's more repulsive all of a sudden. I mean, ridiculous nonsense.
10,000 newtons, or a bit over a ton for my American viewers. The weird thing...
So that's all mv squared nonsense. So all this fake joules of energy. Fake, 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 fake. The only thing anything has that's moving in the universe is momentum. There's just mass moving a velocity. The end. No squared functions.
Is that the force doesn't change as the particles get farther apart. It's basically constant. But, like when you stretch a rubber band, the energy does increase. Once the two parts...
So, bullshit. I mean, just absolutely... He's just telling us this is what we believe. I'm not going to explain why I believe it. Okay, I'm just going to tell you this is what we've decided the truth is. And you might as well tell me you've decided to believe Mohammed was the savior and I should, make prayers every 5 hours or whatever, and I should go to Mecca. I mean, fuck you. You're just making this crap up. Alright, so we'll call that a video halfway, and we'll see if we even decide to come back to this mush. But what a pile of crap. Storytelling, fables, that's all this shit is. Damn. I hate this planet. Goddamn people. It's just so full of shit. You're all so goddamn stupid.